Let's talk about Moore's circle here. And actually, you're going to need some more circle stuff on the homework that's due tomorrow night. Our learning objectives is first to understand what is Moore's circle. Well, it's all the combinations of all possible moments of inertia for all angles of inclination. We need to be able to draw Moore's circle if we're given Ix, Iy, and Ixy. We need to be able to draw Moore's circle if we're given any three of the following, and we'll look at how that geometry works together and how we could do that today. And then use Moore's circle to find the principal moments of inertia and the IU, IV, and IUV for any given angle of rotation. That's what we're looking at focusing on here. Our homework problems are for this one. They're asking us to first pick the correct Moore's circle, to find I max, to find theta p, theta p1 and theta p2. This one, again, we see this I max stuff, theta p1, theta p2 for that shape that's given there. And then again, I max, theta p1, theta p2. So that last homework is really about drawing Moore's circle. And then we can, from Moore's circle, we can find all of the stuff that we need to. So let's jump right in here to our board notes for Moore's circle. Moore was a German engineer in the 1800s, and I don't know how he came up with this, but it's pretty cool when we see how this thing works. That first learning objective, I just want to paraphrase that here. It's a graphical representation of all the possible moments and products of inertia for a shape. So for each shape, for each cross section, we'll have a unique Moore's circle. And the way that we get Moore's circle is that we're going to plot the moments of inertia. And let's abbreviate here, moments of inertia. We'll call it MOI. So we're going to plot the moments of inertia on the horizontal axis. So it's just a graph here on a horizontal axis. And we're going to plot the products of inertia. We'll call that the POI. So moments of inertia, products of inertia is going to be on the vertical axis for our coordinate system. And then we, in order to get the circle, we're going to, on our graph here, we're going to plot 2 points. And these 2 points include IX and IXY, and then IY and IXY times a -1. So basically what we're saying here is we're going to flip the sign when we plot it with IY, and we're going to keep the sign when we plot it with IX. And remember, IXY, the product of inertia, it can be negative, it can be positive, or it can also be 0. So that's in general what we're doing here with Moore's circle. Now, last class, we started this example, and basically we had this C-shaped cross section here. For the X, Y axes at the base here, we had found that IX was equal to 265 times 10 to the 6th millimeters to the 4th. We found that IY was equal to 80.23 times 10 to the 6th millimeters to the fourth. And we found that IXY was equal to 107.52 times 10 to the sixth millimeters to the fourth. And so we did that using the parallel axis theorem, and we had to find the centroid of each segment, and IX prime and IY prime and IX prime, Y prime, and we did all that work last time. Well, what we were looking to find, remember, was two parts here. So for the X, Y axes, part A is we want to find theta P, I max, and I min. For part B, we want to find IU, IV, and IUV for theta equal to 30 degrees going counterclockwise. And so let's draw our U and our V axis on here. So the U and the V, what they're saying is, here's like the U axis would be right there, and the V axis is right there, and this angle would be 30 degrees. So they're asking us to find what is the moment of, in part B, what is the moment of inertia about the U and the V axis. So we're going to kind of start today, even though our original given information was just the dimensions of that shape. We can think about this as our given for today's example. So you think about it two different ways. There's a continuation where given was original dimensions, or for starting kind of a brand new one where our given information is the IX, IY, and IXY. And so if we think about what we're going to do for Moore's circle here, let's go ahead, and the first thing is remember, we're going to put products of inertia on the vertical axis. And our POI, that can be both negative and positive. And so we want our graph to incorporate both negative and positive. Now the moments of inertia, which we're going to put on the horizontal axis, and let's make our graph, make that horizontal line maybe about 2 to 3 inches long or so. And just so we get a decent sized Moore's circle on there. Yeah, probably about 2 to 3 inches long will give you a really nice circle there. So we have moments of inertia on the horizontal, and those are only positive. And so that's why we're only showing the positive side of the graph. But then products of inertia, we're showing both negative and positive, because products of inertia can be negative, they can be positive, they can also be equal to 0. So let's look at our IX and IY. Remember, we're going to plot 2 points. We're going to plot IX with IXY, keep the sign. We're going to plot IY with IXY, and we're going to flip the sign. So the first thing I like to do is just look in general, which one is bigger? Is IX or IY bigger? Well, IX is bigger. And so I'm just going to do a dashed line out here, kind of towards the end of this. And this is our IX. It's equal to 265. I'm going to drop the times 10 to the 6th for all of our stuff here, and then we can add it in at the very end. And then IY, I just know it's something less than that. I'm not so worried about my relative scale on my graph here right now. I'm going to draw it about right here, and that's going to be where IY is located. So there's our IY line is equal to 80.23. So those two lines, the only thing that matters about those two lines, however far apart I put those, is going to tell me my diameter of Moore's circle. If I put those about 2 inches apart, my Moore's circle will have a diameter of about 2 inches. If I put them half an inch apart, my diameter is only going to be about half an inch when we're drawing this on our pieces of paper. Okay, and so remember, these are just coordinates, right? IX would be this distance, like all the way out, and leave some room down here somewhere. But IX would be that distance all the way out to that line right there. That's 265, right? IY would be the distance to that line right there. That would be 80.23. So those are just distances on the graph, aren't they? For Ix and Iy. Okay, now let's plot Ixy. Ixy is positive, so I'm going to keep the sign when I plot it with Ix. And I'm not so worried about, oh, what is 107? How much is 107 on my paper here? I'm just going to come up a little ways. And the main thing is that I do some relative scaling here, because what we just did is we just said, well, that distance right there, that represents that 107.5. So that's our 107.5. And what we did is we said, oh, well, that has a coordinate of 265 and 107.5. That point right there has that coordinate. Now, my other point that I'm going to do is with Iy and minus 107.5. This is the spot where I have to make sure that however far I went above, so I did three grid marks, right? 3 cells above. Let's go 3 cells below, because that distance right there is also the 107.5. And I'm going to do it kind of away from that point over here because we're going to be filling in the circle, but that's also 107.5 right there. And so this point right here that we just did, that's also has a coordinate of, and I'm going to do it up here, that has a coordinate of 80.2 and minus 107.5. So however, that's the only thing I'm worried about is however far apart I put Ix and Iy, that's going to tell me the diameter of the circle. And then however far I go above the axis, I want to also go that same amount below. Now what that gives us then is the 2 points that we need to make Mohr's circle. If I draw a straight line between those 2 points, that's actually the diameter of Mohr's circle, where the center of the circle is where we cross the horizontal axis. And actually that's what we're going to call I average. I average is the center of the circle. Now, if we think about, now we know where the center of the circle is. So couldn't we, and I like to do this with a dashed line first because I get better circles when I do that for some reason. But couldn't we think about what our circle is going to look like? And so there's, now I did a dash line. Now I'll kind of follow my dashes and we can draw that circle right there. Okay, so this circle, what it represents is each point on this circle represents a possible combination of moment and product of inertia for our shape. Now we have to figure out where is that relative to like more circles like this alternate reality. And so we need to figure out, well, how do we tie Mohr's circle back in with reality? Well, let's look at the 2 points that we plotted. Right here is where we plotted the Ix. And so this is our x-axis. That's really representing our x-axis because that's where we plotted Ix. This over here is representing our y-axis because that's where we plotted Iy. So we see x and y on Mohr's circle are actually 180 degrees apart. X and y in reality are only 90 degrees apart. Now, if every point on Mohr's circle represents a possible moment and product of inertia, that means that somewhere on this circle are the maximum and the minimum. The maximum is going to be the point on the circle that has the biggest horizontal coordinate, which would be right there. That is I max. What is the product of inertia at I max? It's 0. We talked about, actually, when we first talked about principal moments of inertia, we thought about it the other direction. We said, if the product of inertia is equal to 0, that means we have maximum minimum. Well, now we're seeing that happen on Mohr's circle, where at the maximum, we have a product of inertia equal to 0. our POI is equal to 0 at that spot. And then our minimum would be over here. I min would be where we have the smallest X value, the smallest horizontal value, and that also has a product of inertia equal to 0. Could you explain how that point is I max? Again, sure, because so this is the x-axis and the y-axis, or that diagonal line on there. And because that's where we plotted ix is over here, and iy is here. So the I maximum, because this is just a graph. And we think about what point on the circle has the biggest moment of inertia, well, it's the far right point right there where we cross the horizontal axis. Okay, so we have I max, we have I min. Well, that means that theta p is going to be this angle right here, except that on Mohr circle, all the angles are doubled. X and Y on Mohr circle are 180 degrees apart. In reality, they're only 90 degrees apart. So what we're going to do is we're just going to call this 2 theta p. This angle over here would also be 2 theta p. So we just say, oh, we're going to still call it theta p so that in reality, it is an angle of theta p. But since everything, all the angles on Mohr circle are doubled, we'll just call it 2 times a theta p right there. Okay, a couple of other things to do with this. Our I average, it literally is the average. It's the center of the circle, and it is equal to the average between x and y. So if we just take ix plus iy over 2, we will find I average, and that's going to be a 265 plus an 80.23 over 2, and I get a number here of 172.12. And so we're not going to do the times 10 to the 6. We'll just remember that at the very end. So 172.12 is I average. The other thing that this is telling us as well is that on our shape here, so Mohr circle, we need to be able to go from Mohr circle onto our shape. We have our x-axis and we have the y-axis. Now, the angles are double, but they go the same direction. So if this angled line, and it's kind of weird because the angled lines on Mohr circle correspond to the horizontal line in reality, to this x-axis right here. So which way do we have to go to get to I max? We have to go clockwise. So that means that our I max is actually about right here on our shape. And then if we go from the y-axis, we can go to I min. So the y-axis to I min, we also go clockwise. So this angle and this angle right there, those are theta p. So in reality, it's only theta p. On Mohr circle, it's 2 theta p. Any questions so far? This is the key part. This is probably the hardest part. The rest of this, if we understand this part, the rest of this is going to be, should be fairly straightforward. And that part is finding those values, right? Because we need to find, how do we find the value for theta p? How do we find the value for I max and for I min? Well, right triangles, even though this is Mohr circle, right triangles are key to solving these. And do you see we have 2 right triangles here? They're the same right triangle. We can pick either one. I'm going to go ahead and pick the one on the top right. There's our right triangle right there. The hypotenuse of this right triangle, like we talked about before, the line there all the way from the bottom left to the top right point, that's the diameter. So that means this is the radius. The hypotenuse is the radius. And actually, let me label, that's that line right there would be the radius from there to there. That's our radius. What about the height of this triangle? Well, isn't that IXY, which was 107.5? And then this angle right here is 2 theta P. If we have two parts of a right triangle, we can find the rest. And that's why the right triangles are key. So we don't know the radius yet, but could we find this right here? Because we know I average, right? We know I average right here. And didn't we find that's 172.12? And so, Mackenzie, what do you think? How could we find the base of that triangle?
Would you just do the Pythagorean theorem?
Well, we don't have two parts yet. We need to find it somewhere. We need to find it from something else.
Would you subtract IX from the average?
Right, absolutely. So we're using Mohr's circle. We're using this picture over here, Mohr's circle, to find the parts of our triangle. So this would be equal to I average minus IX because, or sorry, it's the other way, isn't it? It's I average or IX minus I average because we have IX is all the way out to here. I average is there. And then isn't that distance the base of our triangle? And that would be IX minus I average. So IX minus I average. You could also have found that using the other triangle, you do I average minus IY, right? So lots of different ways to use it to find that geometry right there. And so we're going to get here, this would be a 265 minus a 172.12. And we're going to get the base there of 91.89. Now we have two parts of our right triangle. And so now we can do something like, what about tangent of 2 theta P? Wouldn't that be equal to 107.5 divided by 91.89? And we're going to find that 2 theta P, when we do the inverse tangent, is equal to 49.5 degrees. And theta P is equal to 24.75 degrees. So the 24.75 is the angle that occurs on the shape. The 49.5 is the angle that occurs on Mohr's circle. Because remember, all the angles on Mohr's circle are double. And the way I remember is that X and Y are 180 degrees apart on Mohr's circle, and they always will be. But in reality, X and Y are only 90 degrees apart. Okay, how about now, Mackenzie had mentioned the Pythagorean theorem. Can't we use the Pythagorean theorem to find the radius? So our radius would be equal to the square root of 107.5 squared plus 91.89 squared. And we're going to find our radius is equal to 141.42. Now we can find I max and I min using the radius. Because wouldn't I max be equal to I average plus R? All right, we go from the average, if we're right, so I'm on the far left of the screen here, if we're at the average there, don't we just add the radius because that distance right there, that's our radius, isn't it? So I average plus the radius. So I average is 172.12 plus 141.42. We're going to find that I max is equal to 313.5. Can add the times 10 to the 6th millimeters to the 4th back in. So 313.5. That's our maximum possible. And we also know how we would get there on our shape, right? We're going to go clockwise, an angle of 24.75. So if we inclined our axes 24.75 degrees, that would be the axis where we have I max. I min is going to be equal to I average minus R. And so 172.12 minus 141.42 is equal to 30.7 times 10 to the 6th millimeters to the 4th. Pretty cool, isn't it? That this circle will tell us where I max and I min is. But remember, the right triangle is key. That's where most of our equations come out of that right triangle, don't they? But we need to pull stuff from more circle to get to that right triangle. Okay, let's look at part B now. So we finished part A, right? They asked us for theta P and I max and I min. Part B was IU, IV, and IUV for theta equal to 30 degrees clockwise. Let's redraw Mohr's circle because we're going to use Mohr's circle again. So we're going to redraw the same Mohr circle. And let's figure out where the U and the V axis fall on that circle. So again, we have our products of inertia. I'm going to make it about the same size. Our products of inertia on the vertical. Our moments of inertia on the horizontal. We had this point about right there. That's going to be our IX, IXY. I'm going to do another point maybe over here. That's our IY minus IXY. If we draw a straight line through those, and remember this is the x-axis, and this is where our y-axis was located. Now, if we go back to our original problem statement, they gave us this picture here. They said to go from the, and they usually give us this picture. They said to go from the x-axis, you're going to go 30 degrees clockwise to get to the U. So that's in reality. On Mohr's circle, we're going to go from the x-axis, which actually don't we know what that angle is right there? We know that's 49.5 degrees, right? But from that x-axis, we're going to go not 30 degrees, but 60 degrees because everything is double. So we're going to go 60 plus 49.5, which puts us at 109.5. So we're going to go and we're going to get to 109.5. So let's see where, I kind of want to figure that out. Where is that going to be? Well, it's going to be past this, right? So our total, what I did, I added 60 plus 49.5 to tell me how big of an angle I'm going to go from here. So about 109, wouldn't that maybe put us at about right here or so? And so that's where, oh wait, that looks like 90 degrees from the x-axis. Let's see, we're going like 60. So we could think about from the x-axis, wouldn't that be maybe about right there, right? So there's our u-axis, and down here is going to be our v-axis. And so we know this angle right there is equal to 60 degrees. Now let me trace out the circle, because it's those spots on the circle where those green lines intersect that circle. That's our IU, IV, and IUV. So there's our circle there. And so this point right here, so if we can find that distance right there, that would be IU. If we can find the distance out to there, that would be IV. And if we can find the height of this, if we can find that distance right there, that would be IUV. Or this one over here as well. That would also be IUV. We have, it's still the same Mohr circle. So doesn't that mean that our radius is still the same as before? It's still 141.42. I average is still the same. I average is still equal to 172.12. So it's still all the same circle. It's just a matter of now finding new coordinates on that circle. And again, our triangle is going to be key. Our right triangle, still key. Do we see those two right triangles? There's one on the top left or one on the bottom right. We can use either one. They're the same right triangles. But I'm going to pick the one in the top left there. We know the radius. The radius is equal to 141.42. So that's one part of that right triangle. Can we find our angle? Wouldn't that angle be 180 minus 60 minus 49.5? And for each scenario, it might be different, right? Sometimes we might have to subtract it from 90. We have to look at our Mohr circle and figure it out. So 180 minus 109.5. So that's an angle there of 70.5 degrees. We now have two parts of a right triangle. So we can find the other two parts. The height of this is IUV. So to find IUV, couldn't we use, let's see, wouldn't that be sine? So couldn't we take the sine of 70.5 is going to be equal to the opposite IUV divided by the radius or the hypotenuse? So we can solve for IUV. So IUV is going to be R times the sine of 70.5. Now, what about the base of this though? The base is this distance here. Isn't that the base of that triangle? I'm going to call that, to not confuse it with anything, I'm going to call it D1. Just a random letter and subscript there. I'm just going to call it D1. It's some distance on that triangle. Well, we can find D1 with the cosine of 70.5 is going to be equal to D1 divided by R. So we can solve D1 is going to be R times the cosine of 70.5. But what is IU and IV from D1, right? Because D1 is not IU or IV. Isn't IU, if we look at our circle over here, wouldn't it be I average minus D1? Because we know where I average is. We can just subtract D1 there. And then we can find IV would be equal to I average plus D1. The key is remembering that X and Y on Moore's circle are at this angle of 49.5 degrees. And so when they tell us to find U and V, it's that 60 degrees is relative to the inclined X and Y axis, not from the horizontal axis on Moore's circle, right? Yes, and then I see a question in the chat here. Will U and V always be across from each other like the X and Y? Yes, because U and V are always going to be 90 degrees apart in reality. And so that means on Moore's circle, they will always be 180 degrees apart. Good question. Any other questions? And I've got one more thing that I want to do, and that is to look at all the possible scenarios. And I think this is really helpful because we can think about what different Moore circles might look like for different problems. And those scenarios just relate to the relative value between Ix and Iy. So, and this is the one that we just did. We did Ix is greater than Iy, and Ixy was positive. And so that one had this Moore circle. And I'm going to do these kind of quickly here, where basically it looked something like this, where we had the x-axis here, we've got the y-axis here. This is our 2 theta p. We can draw our circle in there. All right, this is I max is right here. I min is right there. And if we have some blob, let's just call our shape some blob, X and Y, then to get to the maximum, we go from the x-axis, and I max is down here. So from the X, we go clockwise, we get to maximum. From the Y, we go clockwise, right? So from the Y, we go clockwise, and we get to minimum. And that's an angle of theta p. So 2 theta p on Moore circle, theta p in reality. Let's change it up a little bit. What if we still had Ix greater than Iy, but now what if Ixy was negative? So, we have a shape where Ixy is negative. And, this can be whatever Ix, Iy, and Ixy we start with, those are the coordinate system that we're going to use for Moore circle. And that they could have asked us for the centroid of the composite. Or like in this example, we were using the bottom left corner, right? So we have the Ix, Iy, and Ixy for this bottom left corner. Now, I could have given you the Ix, Iy, and Ixy for the centroid of this. It would be different numbers, but we would go through exactly the same process for Moore circle. So parallel axis theorem does a transformation between axes that are parallel. Moore circle does all the inclinations for whatever axes, for whatever origin we're looking at, for wherever the origin of our coordinate system is working. But Moore circle works for any origin of a coordinate system. It could be at the bottom left corner. It could be at the centroid. of the composite. It doesn't matter where the origin is, but Mohr circle will give us that for all those, for all that information. Okay, so for this one, we have our plot here, our graph. And let's see, Ix is still greater than Iy, so that means Ix is going to be over here. But now Ixy is negative, so that is going to put that point down below. And then with Iy, we flip the sign, so that means that the Iy is going to be over here. So what we end up with is a y-axis up here and an x-axis down here. So if we have our shape that's just a blob, and we have the x-axis and the y-axis, which on our shape are pretty much always going to be horizontal and vertical, well, how do we get to maximum and minimum? Well, if we go that way, 2 theta p, that's going to get us to that I max point, which would be like right here. So we go x, we go counterclockwise, and that's going to get us to I max. Or we go from the y, we go counterclockwise, and that's going to get us to I min. So that means that I min is here. So we see that I max and I min are always going to be 90 degrees apart. In reality, 180 degrees apart on Mohr circle. What if we have Ix is smaller than Iy, and let's look at Ixy as positive. Now, if that's the case, now we're going to have Iy is going to be out here, and we'll have Ix over here. Ixy is positive, and that goes, we keep the sign with Ix, so that means that's going to put that point there, and then Iy is going to be here, and so we're going to end up with our y-axis is here, and our x-axis is there. So doesn't that mean now for our shape that to get from to the maximum, wouldn't we go 2 theta p from the y-axis? So we're going to go from the y-axis, and we're going to go counterclockwise. So that means that I max is now here. To get from the x-axis, we're going to get to the I min by going that direction. So that means I min will be right there. Could you all imagine this? What would change on this if Ixy was negative? Wouldn't the line go from going like this to going like this, right? Wouldn't this point, I'm just going to do it in purple, wouldn't this point move up to here if Ixy was negative, and then this point would move down to here? But now you'd have a different direction to get to maximum and minimum, wouldn't you? Now, some of the other scenarios would be like Ix equal to Iy. And we're out of time here, so I'm not gonna do those, but those are the 4 main ones right there that we're gonna see. Now we could have Ix equal to Iy, that's kind of rare. It just means that the line is vertical. The other one we can have is, what if we have Ixy equal to 0? Well, doesn't that mean that we're just, if Ixy is equal to 0, then we have an x and a y here. Basically, then theta p is equal to 0. Okay, that was what I was hoping to get through today.